today, as I said, we have a very special session because it's not me, so you don't have to cope with my face and voice. We have a really very special guest, Dr. Eloïse Gaillou. She's a PhD, so she's a brain. She's a research scientist from France. She made her master's in geology and petrology at the University of Nantes. And then she started a PhD, which is the doctor's thesis, and she wrote it on opals, on precious opals. And I think I met her in San Diego, California, on a GIA symposium, precisely when she was doing the PhD with Emmanuel Fritsch, the professor Emmanuel Fritsch, the very famous monstre sacré, which is the sacred monster. Maybe it doesn't sound well in English, but in French sounds really well. So he's like a monster in the good sense of research gemology. And so she at the same time she was doing the PhD, she was doing the DUG, which is Diplôme d'Université en Gemmologie. So it's a university diploma in gemology, really high ranking and highly regarded diploma, scientific diploma in a qualification in gemology, really top. The best ones are DUGs. And when I meet the DUG, I do like this because they are really amazing. And then she went to the Smithsonian, that fantastic museum with one of the best, if not the best, gem and mineral collections in the world. And she was doing research on colored diamonds in there. And she will tell you all about it. And she could handle those famous diamonds that we only see in pictures and behind a very thick glass. She could handle the Hope diamond and all those goodies. So she was really lucky. And she was doing some more postdoc, post-PhD research in the Carnegie, also in Washington, D.C. Then she got a position as assistant curator in the Los Angeles Natural History Museum, working with Tony Kampf. And then in 2015, she decided to return to France, and she is curator of the Mineralogy Museum of the mining of the l'École des Mines, the mining school in Paris. Maybe then I always make mistake on the name of this museum. It's a lovely museum. She will show you a few pictures of the museum, and you will be given also the link for their Instagram accounts. So after I say just one or two things, I will call Eloïse to join us. And for the time being, at the end of this session, you will have, as usual, a poll where it's like a quiz. And Eloïse will guide you through that quiz to make sure that the most important learning outcomes, if you want to call them learning outcomes, you take them away, you take them home more consolidated. And also at the end, you see a button there with the Q&A, that's a questions and answers. And anything that you wish to ask Eloïse, she's the real expert, not myself, make sure you type it there. And at the end, during the session, we will try to reply, she will try to reply to the easy questions and the difficult ones, because she can do the difficult ones today, not me. And also in the end, I will post on your chat log the links for the next session and the links for further reading that Eloïse, she made a selection of further reading for you guys, so you can study some more things on diamonds if you wish to do so. Anyway, tomorrow, all of you will receive an email, like a thank you email with all those informations as well in your email box. So you don't need to worry that you will catch the links at the end of the session. Also, I can tell you right away that the next session will be on Tuesday, as always, 10 o'clock, 6 o'clock Lisbon time. And the subject will be rubies and an historical review. So, having said that, I would probably call Eloïse to join us. Where are you, Eloïse? Yay!
I'm here. Hello, everybody. Thank you for joining. So I see people from all around the world, so that's very sweet. Thank you very much. So just special thanks to tous les Français qui nous regardent, les amis, la famille, and of course, everyone I know. I see a lot of people from Washington, D.C., for example, from the Smithsonian and from Carnegie. So that's really sweet. Thank you very much for joining. Thank you, Rui, for doing this sessions of webinars. Please keep on going and entertain us and educate us at the same time. Thank you.
Yeah. No, I thank you. I mean, it's a privilege to be able to have a real expert. As you guys see, I have books behind me. So when people listen to me, they think, he must be educated. But the real experts like Eloise, she doesn't need any background with books. So that's the difference between a wannabe and the real thing. So before we start, Eloise, I would, because you are going to speak about colored diamonds and all the science behind it, I would probably start just discussing what is the word that usually people don't call them colored diamonds. We hear fancy colored diamonds. So I will just spend 2 or 3 minutes explaining the word, because I had this pain point. You are not a native of the language, me neither. And when I first heard the word fancy, I thought it was like a technical term. But it happens that in English, fancy, it's used for many things. You have fancy restaurants, you have fancy clothes, you have fancy hair, you have fancy anything, and also a fancy color out of the ordinary, or a fancy shape. Curiously, the diamond dealers, they use the word fancy shape when they want to refer shapes other than rounds. So the fancy word is also used for shape in diamonds, not only for color. When it comes to color, actually the GIA, the Gemmological Institute of America, this benchmark for the color grading and the grading of diamonds. The diamond grading system, the so-called International Diamond Grading System, is from 1954. Grading fancy color diamonds was a bit later, but they are benchmark. So they define fancy, or a fancy color, in a very strict way. For example, some of you know, some of you that have seen the diamond report, and you see that the color of diamonds is communicated with letters from D, E, F up to Z to assess that colorless and near colorless letter or grade of diamonds. You pick up a diamond, which is here. I just went to the Tower of London and took this. And to assess the color, you don't do it face up. You compare the color of diamonds by the side. So you have like this one, and then you have a master, and you compare the color or the tint of this diamond seen from the side with certain viewing conditions. And curiously, you do this for yellows, for browns, and more rarely for grays. So any yellowish, brownish, or grayish diamond that falls within those masters from D color up until Z, and Z is the frontier with fancies, so they will receive not a fancy grade, but a color grade. They can have color descriptors like faint, slightly light, or very light, but no fancy grade. But when they cross the Z, then they can receive a color grade. And any color, not only the yellows, the browns, and the grays, but any other color like blues, greens, purple, pinks, reds, violets, they can receive a fancy grade if they have a perceptible color, but not from the side, but face up. So that's how you grade fancy colors, from the face up. That's why cutting is so critical in fancy color diamonds. And Eloise, she will explain that to you with a really famous example ahead. So I think I'm done for the day, Eloise, and I will pass the microphone up to you. Thank you very much for having the time to be with us tonight. And I'm sure that everybody will love this. So thank you very much. I will kill my video now.
No, we have to allow me to share my screen. I cannot right now. So you have to do something.
Oh.
Magic happened. And
yes, I know.
Because when Rui says he knows nothing, he actually knows much more about grading diamonds than I do. So, because I don't work for a lab, okay? I work in a museum. So really I see this colored diamonds more in the scientific point of view and not in the really lab point of view. However, I will show you a few things about that later though. Here we are. So Rui asked me to put a few pictures of the museum I work for, and this is the museum, the School of Mines Museum in Paris, indeed, called ParisTech. I know it's really difficult to pronounce. But today, I'm not going to be talking about geology of diamonds. However, I want you to know that you have a great lecture done by Evan Smith from last night from GIA, and it's available on the GIA website. So if you want to know more about geology of diamonds, please go ahead. And that will help a lot to understand what's happening in those colored diamonds as well. So first of all, what I want to tell you is why we are talking about colored diamonds today. Why is it important? Well, if we were like 30 years ago, something like that, colored diamonds would not be as important as they are right now. They were mostly connoisseur stones. And I know that Alan Bronstein is in the house tonight. So hi, Alan. And he was one of those connoisseurs who knew a lot about colored stones already. But since then, the knowledge about colored diamonds and the price and the will of wanting colored diamonds has increased tremendously. And that's one of those famous diamonds that reach record prices at auctions not that long ago in 2015. It's called a Blue Moon of Josephine now. It's a type 2B diamonds, and it's 12 carats, 12.03 carats. It was sold for $48.4 million at a Sotheby's auction back then. So that's $4 million per carat, US dollars per carat, okay? So that's actually the most expensive gemstones per carat ever sold at an auction. So I will show you, this is the rough. It was about shy of 30 carats here. And you see that the color is not as intense as in the cut diamond. But that's the magic of a diamond cutter to make and to enhance, to naturally play with the facets and make the blue much stronger in color. Indeed, they're the most precious of all the gemstones. And here we had the chance, before it was called the Blue Moon of Josephine, it was only called the Blue Moon. It was owned by Cora International, and we had the chance to receive it from Cora with the help of Alan to study it at the Smithsonian Institution, to make some research on this diamond, and published a paper about this diamond. And also afterwards, we exhibited at the LA Museum, Los Angeles Museum. So hi again to the colleague from there. Another great stone, incredibly, like it's 59.6 carats, so big, nice color. It's a fancy vivid pink diamond. So fancy vivid, you will see later, that's the color grade that you want to achieve in a colored diamond, fancy vivid. This one is internally flawless, and it was sold for $71.2 million US dollars. So this makes it the most expensive gemstone ever sold at an auction. So the most price per carat, the most price for a gemstone, and that was achieved by 2 colored diamonds. So why is it so important then to study and to know color in diamonds? Because, well, if we know we have natural diamonds, but we also know that we have natural but treated diamonds, and that we also have synthetic diamonds that can be colorless or all kinds of colors that you want. So to truly be able to identify and to make the difference between a natural and a synthetic and natural but treated, you will have to understand exactly what happens in a colored, natural colored diamond, and study the synthetics and the treated as well. So that's why a lot of research have been conducted on those, because of course, if they didn't reach such crazy prices, maybe we wouldn't care, but nowadays we do care. I want to show you some basic information about diamond and then after grading. And to begin with a diamond, this is a rough octahedron diamond. It has not been faceted. That's truly how it comes in the earth. So diamond is a mineral. That means it's a crystalline solid, and it's only composed of carbon, only carbon in its structure, and it crystallizes into the cubic system. However, you don't usually see cubes in the rough form. You mostly see this octahedron shape that I was showing you earlier. So I don't know if you see my mouse right now. This is the octahedron shape typical for a diamond. You have some derived form as well, but they are not as typical, and sometimes those aren't necessarily gemmy. Just for your information, the largest diamonds, what we call the type, and sometimes the type 2A diamonds, they don't really show such a nice shape. So here is a diamond, it is host rock, this is a kimberlite, and this is the rock that actually brought back the diamond at the surface of the earth, because diamonds form very deep inside the earth, again, referring to Evan Smith's lecture on GIA website. But I just want you to know that it needs a lot of pressure, a lot of temperature. Diamonds form at least 150 kilometers deep, okay? So that's a lot of temperature and pressure there. At this pressure, well, the structure makes this mineral made of carbon having a really dense, compact structure. So yes, it's only carbon, but the carbon atoms are really close together. And it makes these diamonds really hard, actually the hardest material existing on Earth. And only a diamond, another diamond, can scratch a diamond. So that's why you cut and polish diamond with diamond grains. The problem with diamond is, yes, it's hard, but it has a point of weakness. And this is what we call the cleavage. And you see the picture here of a cleavage, and you see that it follows the face of the octahedron. So yes, it's hard, but if you drop it on the wrong angle, it can just break into two, the hard floor from height. Diamond always contain defects. So I was telling you, yes, diamond is pure carbon. Well, nothing in pure is pure in nature, or even in a lab, to be honest with you. In nature, sometimes you have some missing atoms in the structure. That's really common in diamonds. Or sometimes you have carbon atoms that are gone and that have been replaced by other chemical elements. So typically, not all elements can enter the structure of the diamond, because I was telling you, you don't have much space in there. So typically in diamonds, the main impurity in diamonds, really common, is nitrogen. So this is a chemical element, light element. Or the second most impurity is hydrogen. And the very less common one is boron. You have other impurities, but they won't really matter, and they don't have a big impact most of the time in the color of diamonds. So in gemmology, you probably heard about that if you have been, if you want to be into diamonds a bit, you know that diamond is defined by the presence of nitrogen inside the structure. So you always think and hear about types of diamonds. So you can hear about type 1 and type 2 diamonds. So type 1 diamonds contain nitrogen as visible by infrared spectrometry. And this is a method that is used standardly in gem labs, and non-destructive, superflexive, safe. 99% of gem diamonds fall into that category, versus type 2 diamonds that do not contain any nitrogen as visible by infrared spectroscopy, and those diamonds are really rare. Within those two categories, you will see you will have subcategories. So for type 1 diamonds, you will have diamonds that contain nitrogen as isolated elements inside the structure. That's what we call the type 1B diamond, so isolated nitrogen. Or after that, you have the type 1A diamonds, and those diamonds have nitrogen but aggregated. Why is that? Well, to begin with, when the diamond grows, and if it has nitrogen impurities, it will get into the structure. But as I was telling you, diamond is formed deep in very hot and under a lot of pressure, and it stays for a long time, most of the time. A lot of diamonds are between 1 billion to 3 billion years old. Yes, they are really old. And over all of this time spent inside the earth mantle, well, nitrogen has the time to aggregate and to come together, forming pairs or 2 or 3 nitrogen or 4 nitrogen. So that's how we define subcategories within the type 1 diamonds. Type 2, I will show you just after, but let's go back to all the different kind of colors that you can have and on the different types. Type 1A, I was telling you, these are the diamonds that contain aggregated nitrogen, meaning that they're not young, they're pretty much, they can be in the old category. Versus type 1B diamond with isolated nitrogen. These are younger diamonds, versus the type 2 diamond. So you have the type 2A for no nitrogen and no other impurities, and they can cover a wide variety of colors as well, as you see here, versus the type 2B diamonds. They do not contain any nitrogen, but they do contain boron inside the structure. And those diamonds are the rarest. The color of those diamonds are from colorless, near colorless to gray to blue. Just to come back to what Rui was telling you earlier, how do you grade a diamond? This is nice, another nice blue diamond. You will see I like blue diamonds, so you will see a lot of them. This is the Oppenheimer blue, and it was a record as well. 14 carats sold for $50 million, 2016. It's not nothing. And you see that the color is pretty intense because it's not thanks to the shade that you can see this intense color. So I'm sure the rough was quite impressive as well. How to grade a diamond? Well, in first place, even colorless diamonds are graded by color. It's not the only criteria, because you probably know that you grade diamonds with the 4 C's, but the first C is color. So you want this diamond here on the left, which is a D color, which is the perfect or almost perfect colorless diamond. And to show you the difference in price for beautiful colorless diamond, flawless, this one is 118 carats, and it was sold for only $31.8 million. Okay, I say only, okay, but just realize the fact that it makes this stone worth $269,000 per carat versus the 4 millions for the blue diamond, okay? So we're not in the same price range here. So first C is color, and then you have the clarity. That means does it have any inclusions, for example, or not? Obviously, you want something that has nothing inside it. The carat weight, the bigger the better, and a nice cut as well. So the light comes through nicely. And there's another criterion that is used in labs right now is the fluorescence. The market right now doesn't like to have diamonds with a strong fluorescence, because when you go outside in the sun, you might see your diamond glow a bit, or it makes it a bit milky, and that's not suitable for the market. Personally, I find it very nice to have a glowy diamond, but that's not what the market wants. And actually, that's a very important point here, is that for colorless diamonds, such as the one on the left, or those ones in the center mostly, it's pretty standardized, okay? When you have big stone, they are on the side, but for stones from less than a carat to 5 carats, it's very standardized. You can basically buy it just by looking at the reports, just the letter, the scale, the clarity, the carats, and the cut, and you know what to expect. That is not the case for a colored diamond. So how do you switch from a scale that is not suitable? Basically, all those light yellowish brown, which is very common in diamond, you can switch from a light color not suitable to a fancy color, this fancy word, the grail that you want to obtain for colored diamonds. Well, you just need something more intense than just the regular light color. And the best color that you want to achieve is the fancy vivid. It has nice intensity, it has nice saturation, it has really everything. And actually you can play with that. Sometimes you can take a diamond that is not great in color, such as this over 6 carats brilliant diamond. The brilliant cut was not perfect for this diamond, and it has been repolished into a 4.6 carat stone, and you see that the grade is now different. From a S to Z color, it has been switched to a fancy yellow. So you are now in this category here, and now that's a suitable diamond for the market. Okay, so more about really color, grading the color. In colored diamonds, the most important thing is the color. So, and you will use a lot of terms to actually define that color. You won't care that much about the clarity, actually not much at all. About the carats, yes, sure, but it's not primary. And the cut, again, sure, as long as it enhances the color, it's fine, but otherwise it doesn't truly matter. So we'll talk first about the hue. The hue is, what color is it? Is it yellow? Is it pink? Is it green? Does it have another component? Is it brownish yellow? Well, if it's brownish yellow, it has another component, and the market, again, doesn't like that as much. Is it greenish blue? Again, you want pure colors instead of mixed colors. So that's important. The tone here on the vertical axis, well, it's more about the darkness of the stone. Is it light in color versus dark? So that's the amount of black, if you want, inside your stone. Versus the saturation. The saturation, you would go from light to intense. That's the intensity of the color. Okay, so you will have a bit of color or you will have a lot of color. And you'll see at the intersection of all those weights, terms, you will find the fancy vivid. Again, fancy vivid is the best color that you can achieve. So Rui was talking about that earlier. That's what you use, that's what is used at the Laboratoire Français de Gemmology. And I can say hi to my colleagues over there. And this is a master, this is some pieces from the masterpiece here, and you see the diamond they're trying to grade here. So you have usually masterpieces to compare a colorless diamond with others, so you can attribute a grade, a letter. The problem is that we don't have such master pieces for colored diamonds. They don't exist. We don't have suites of colored diamonds. So what we have to do is to compare with colored existing, for example, here online, it's called the Gemmy Wizard. That's what they use at the French Gem Lab. And they just compare it with that. And usually it's not only one person that makes a decision, it will be several people grading one colored diamond. At GIA, they use this system here with a bunch of different little balls, colored balls, and compare it with a gem. Okay, so I thought that was interesting and really important to know. And now we can go into the color of natural diamonds only. I'm not going to talk about treated or synthetics, only natural today. So this is the beautiful aura butterfly of peace. I think it's the best example to show you the variety of color in diamonds. This is my photo, so it's not the best photo of this beautiful collection that is owned by Alan Bronstein, but still, I think it really nicely represents the variety that you can see. So the first thing I want to tell you about colored diamonds is that the color in diamond is always due to those impurities that I was telling you about earlier. They're not due to coloring agents. So maybe you have heard before that copper can give color in the minerals, copper, titanium, iron, manganese, cobalt, you know, like if you know a bit of your gemstones, you will know that chromium gives the red color to ruby, or to iron and titanium gives the blue color to sapphire. This is not the case for diamonds. Diamonds are colored by another process that is called color centers or point defects. And it means that those some single impurities, elements, are colorless to begin with, but that the fact that they are introduced into the structure will give rise to a distortion of the diamond structure. The diamond is not going to be completely pure as it was before, so it has to accommodate to welcome this new defects. And then this accommodation makes for lights to be absorbed and give specific absorption, and then giving rise to color. So if you didn't follow me here, don't worry, because I will show you some example later. But here it is. Point defects are the coloring agent for diamonds. And then we'll go into specific. So let's begin with bright diamonds, because I want to go from the more common colored diamonds to the rarest. And you will see I will tell you when they will begin to be rare. Brown diamonds are not rare. They are actually the main diamonds on Earth are yellowish to brown. So that's what I was showing you earlier, the ones that you don't really necessarily want. However, fancy colored brown diamonds with a nice intensity, they're a bit rarer though. The first diamond that we heard about that was brown in color was the Golden Jubilee, because it was big. It's the largest diamond, cut diamond ever found, ever faceted, I think. It's 547 carats. It has been graded fancy yellowish brown, and it's a type 2A diamond, so without any nitrogen visible by infrared spectroscopy. And it comes from the premier mine in South Africa. This mine that has unearthed so many large and beautiful stone. A lot of type 2A diamonds come from this mine. And this was cut in the 1990s, I think. And it's only from that time that brown diamonds came into the market. Before that, basically, brown diamonds were just grounded to be used as material to polish. They're not used in jewelry at all. So all of the smaller brown diamonds, they will just be destroyed. However, when the Argyle mine in Australia opened in 1986, they uncovered a lot of brown diamonds. Most of their production, over 99.9% of the production, is brown diamonds. They don't have any colorless diamonds there. So it would be a shame to throw all those diamonds away and to use them in jewelry instead. So they began a marketing campaign, and this marketing campaign didn't use the word brown, it used the word champagne, cognac, or chocolate diamonds. And here is a nice brooch from the Smithsonian Institution with 61 carats of diamonds in total. And I think that you see very well the range of all brown color that you can achieve, from light to deep, from champagne to chocolate. About the color of brown diamonds, I would say that over 90% of brown diamonds follow this rule, is that the color is due to plastic deformation. Okay, that's a big word here, plastic deformation. What does that mean? You see here in this picture that this diamond is zoned in color. The color is not homogeneous. Well, that is because the diamond had to readjust its structure while it was placed under a lot of strain. So inside the earth mantle, basically this diamond to begin with was maybe colorless. Actually, it was colorless because you see some colorless areas. It's only after it grew that it got its color. And that process is due to plastic deformation. Plastic deformation is just the state before breaking. Actually, under high pressure and high temperature, a diamond cannot break. It's just basically rearrange its structure and adjust to the strain. And that rearrangement is following the cleavage plane, actually. So basically what's happening is that the atoms are moving, really the atoms are moving following the plan, the cleavage plan, and then basically you can have defects forming at this very specific area. So that's, in gemology, we call that the graining. Graining can be colorless, brown, or pink most of the time. I will talk to you about that a bit later on. So that's what plastic deformation does to a diamond. Doesn't break it. Just before the breaking, it's rearranges structure. On the left, you see, for those interested, absorption spectrum showing you the absorption of a brown diamond. Well, you see only a continuum going from the UV, the ultraviolet, to the infrared here, and no specific absorption, only the continuum of absorption. That's what gives rise to the brown color. Okay, but what is the defect exactly? I was telling you about defects, color centers. What is this? Well, in this case, see, it's not a specific element at all. It's the fact that the diamond is missing some carbon atoms that gives rise to specific absorption, therefore to the color. In this case, at the slipping planes, the gliding planes, it's managed to actually, the plastic deformation managed to remove some of the carbon atoms, and models show that missing atoms, 40 to 60 missing atoms is enough to give you per like you need a lot of them, but locally you need 4 to 60 missing atoms to give rise to some color in brown diamonds. That's a color center with missing atoms. Okay, so that was from the most popular, well, the most common diamonds, brown diamonds. Now, black diamonds, yes, because black is a color, right? So one of the largest black diamond in existence is the Orlov diamond. It's really well known. It has been sold just after it was shown at the Natural History Museum of London. So it was sold in 2006, and it's big, 67.5 carats. I really like this picture. It's not all black diamonds that look as nice as this one. But what really make black diamonds famous is this the jeweler called de Grisogono, by purchasing and making this ring with a 312 carats black diamond. It's huge. Can you imagine have like a ring like this that's high when you wear it? It's insane, but it made people, the press, talk about him. And right after that, and we're talking about in the 1990s, the end of the 1990s, and right after that, he began a new line of jewelry using smaller, very small, what we call pavé black diamonds here. And nowadays, it still continues this line. So I have to tell you something about those black diamonds. I will show you right after the origin of the color in natural diamonds, but to let you know, to begin with, a lot of the pavé diamonds, black diamonds used in jewelry are heated in the first place, and that's by heat treating them, we can manage to turn a diamond black. Again, I'm not going to go deeper into the treatments, but I wanted you to be aware of that. So that's what a natural diamond look like. Most of the time, it's not black. It's actually just dark, very dark. This is a brown, dark, very dark diamond. Only if you put a fiber, optic fiber underneath that, you will see that it's brown. It's just deep, deep, deep brown, and it looks like it's a black diamonds. That's very common for black diamonds. And here I'm only talking about monocrystalline diamonds and not the polycrystalline diamonds that, like, I know that this morning a lot of people mentioned that, not the carbonado diamonds. These are not carbonado diamonds, really these are single crystals. Most of the time as well, you have some diamonds that are heavily included. You see a lot of ugly inclusions. Again, this morning I had a question like, what about those salt and pepper diamonds? Well, these fall into this category with a lot of inclusions, either black or whites, and they give you either this dark diamonds or sometimes gray, and very heavily included diamonds. This is where the story for black. Oh yeah, this ugly spectrum here to show you that there's nothing to see in the UV visible spectrum of black diamonds because all the light is absorbed, pretty much nothing to see. White diamonds. See, earlier at the beginning, I was telling you about colorless diamonds. I never talk about white diamonds, only colorless diamonds. It's because white diamonds, they do exist. And these are nice examples from the Aurora collection. They have this milky aspect. So we can call them white diamonds, milky diamonds. I call them opalescent diamonds because they show this milkiness that in gemology we call opalescence. They are truly beautiful, and I think that right now they're not appreciated for what they are. Maybe it's a good thing because that means they're not that crazy expensive yet, but people begin to be more aware of those. Especially there are a few papers that came out recently about those in Gems and Gemmology. You will have the reference about those later. They are colored with tiny little inclusions. So these are inclusions that you cannot see with your eyes, you cannot see with a loupe, a binocular. You need a very specific machine to see it. It's called these images that you see here are were acquired by microscope, transmission electronic microscope. Sorry, I had it in French. And basically with this kind of machine, you could even achieve to see single atoms. This is crazy. So you have to really look at tiny little things. Those inclusions are about 20 to 200 nanometers in size. Very tiny, you won't be able to see them. However, the lights, when the light arrives in these diamonds containing those inclusions, they will be diffused. The light is going to be diffused, making this milkiness. It's got just drop a single little drop of milk into your water, and you will see this milkiness appearing. Your milk disappeared into that tiny little spheres, if you want, and now you have this milkiness aspect to it. That's what really happens. Now we begin with the rare diamonds, the rare, really rare diamonds, with this nice, fancy, vivid yellow diamond that was sold at Christie's for $3.6 million in 2015. That's the largest diamonds I think ever sold at an auction for such an intense price. And you'd see, I will put another picture here to compare with this 20 carat stone that was sold for over $5 million. This is actually the most expensive yellow diamonds per carat ever sold at an auction. Now you see the difference in, maybe in the color, you will see both of them are vivid yellow. However, the cut is completely different. On the right, you have a cut that has a lot of facets to enhance the natural beauty of the stone, while this one on the left didn't need any enhancement, and just a regular rectangle cut is enough to show the beautiful color of the stone. Actually, two facets would have it make it maybe a bit too deep actually in color. So again, you want to achieve the vivid yellow. So that's the job of the diamond cutter. Most of those yellow diamonds are called Cape diamonds. Why is that? Because most of those diamonds are colored by what we call the Cape color center. So what is the Cape color center? It's this line at 450 nanometers that absorb in all this range. This is the same scent here, and that only allows the yellow color to be transmitted in this region here. So what is it? Well, it's 3 nitrogen atoms around the vacancy. I was telling you earlier about those color centers, those point defects. Why we call them point defects is because they're really punctual inside the structure. And again, nitrogen doesn't have any color by itself. Nitrogen is in the air, you don't see it. But by its presence in such aggregation in the diamond, it will give rise to this specific absorption here, therefore the yellow color. Most diamonds are of this type. Really rare diamonds are called the canary diamonds, and they fall into the type 1B category, meaning that they are colored by isolated nitrogen. So the previous one, the Cape diamonds, to give a good color for, depending on the size of the stone, obviously, because the bigger the stone, for the same concentration of nitrogen, you will have the bigger stone is going to be more intense in color versus the smaller, okay, for the same quantity of nitrogen. But usually for Cape diamonds, you have about 500 to 5,000 ppm of nitrogen. However, for type 1B diamonds, you can have only 100 ppm of isolated nitrogen, and it's enough to give you good color. So canary diamonds are it's a much more efficient color center inside this diamond. So again, see, just 1 nitrogen every so often, carbon removed out of the structure, and this is what gives rise to the yellow color. So that means that those diamonds are actually younger, because remember, isolated nitrogen, meaning that the nitrogen didn't have the time to aggregate yet. They're younger than the Cape diamonds. Most famous yellow diamonds in existence, I think, is the Tiffany, 128 carats. It has been graded by GIA, but we didn't have the report, so I cannot tell you if it's a type 1 or 2. I think it's a type 1A, but not sure. The first time really heard about it was when Audrey Hepburn wore it for the promotion of Breakfast at Tiffany's, and the latest time that we saw it was on the neck of Lady Gaga for the Oscar last year. Okay, what about pink diamonds? And now we're really moving into much rarer diamonds, okay? This is the great diamonds, the sweet Josephine diamond. So maybe you remember the blue moon of Josephine? I think I didn't tell you earlier, but the blue moon of Josephine was actually bought by Hong Kong billionaire Joseph Low, and he purchased it in 2015. And the day before he purchased this most expensive diamond, he purchased this one for his daughter again and named it after his daughter. So the two most expensive diamonds, basically, that he could buy, he put them in 2 days. It's quite a stone, 16 carat for $28.5 million. So when I talk about pink diamond here, it falls into the category, the red diamonds and the purple diamonds as well. It's the same category. I will show you why in a little bit. Okay, pink, or this color red, the Musée red, is only an intense pink. When the pink is really intense in color, it's called red. And actually you see in this photo that it's kind of, you know, a bit pink. This is actually the largest red diamond in existence, cut diamond in existence. It's 5.11 carats. It's small compared to those diamonds that we've seen before, okay? The red diamonds are so rare, they never come in big size. So that's really something. There's another color of red. It's the young red from the Smithsonian Institution. And this one has a reddish brown component to it. And it's a fancy dark. Indeed, at the Smithsonian, it's shown under a strong light to be able to see the red color. And I was telling you purple. I'm going to show you this, this gem because it has a lot of impurities inside. You'll see those things running through the stone, but it's purple. And believe me, I've done a lot of research on the internet. I've never seen a diamond graded pure purple. It doesn't have another component. It's not a brownish purple. It's not a purplish pink. No, it's a purple. That's really rare for a color. So we don't really care about the fact that it has inclusions inside it. But the origin of the color is the same for pink to red to purple. And most of the time, the origin of the color is due to what I was telling you about earlier, is the graining, this plastic deformation that can happen when the diamond is still in the earth mantle, very deep inside the earth mantle. Here you have a nice suite of Argyle diamonds, this mine in Australia that will finish producing, I think this year or next year. And this is their production of the best diamonds for the year 2019. They range from 1 carat to 2 carats, and they have 2 red, one here and one here. So you see the production of the year for good quality stones. This is it here. And actually each year they put a trade, which is called the tender Argyle pinks, showing and selling all their best diamonds. You see again a purplish pink, and this time the purplish pink comes a lot from Russia. And you see it's not a perfect pink, it's not a perfect purple, it's in between. We know that the color comes from the absorption, this absorption here at about 550 nanometers, that only allows the transmission of the red. You want a really intense band here to actually have a stronger color here. But yes, we know that this thing absorbs, but what is the color center exactly? I cannot tell you. We still don't know. All I can tell you is that it most likely involves some nitrogen and some vacancies, some holes inside the structure of the diamond. But what is the combination? What is the number of nitrogen around how many numbers of vacancies? I cannot tell you. People have worked on that for that many years. I think I worked on that for almost 10 years and still not discovered that answer. I'm not the only one doing the research, by the way. Okay, most of the time you will see some color zoning, such as in the brown diamond. For Argyle diamond, the color zoning is not going to be as strict. It's going to be in wavy bands like this, while in other diamonds, pink diamonds from other places around the world, like Russia, for example, you will see this perfect lamellae, and in between the lamellae, pink lamellae, you will see a colorless colorless areas. Again, that's due to this plastic deformation here that made those planes, and within those planes during the deformation, something happened and a color center was created. You have some really rare pink diamonds that are called Golconda because they're type 2A diamonds and they do not have graining. The color is homogeneous. And these are colored by what we call the NV centers. So the NV centers is usually a color center created during irradiation, natural irradiation in this case, okay? Natural irradiation, and only the red is transmitted here. So these are 1 nitrogen plus 1 vacancy. That's the color center involved. And actually this color center gives rise to fluorescence as well. I was chatting with someone earlier about that. So when you look, you put a UV light, these diamonds fluoresce orange. What about violet diamonds? Violet, I'm not talking about purple because purple is a combination of pink plus green, plus red. Oh my God, I do that all the time. Purple is a combination of pink plus blue. Violet, it's a color by itself. And those violet diamonds, they only come from one place around the earth, is from the Argyle mine, again in Australia. This is actually a suite from bluish gray to violet diamonds. It's never perfectly blue. There's always a gray or a violet component to it. Only rare stone achieve the violets, this violet color. So this is one of them here, reaching the violet color, pure violet. Usually it's, here again, grayish, bluish violets. That's pretty common, but the violet, the pure violet, is really rare. Again, you see the size of the stones, small. We don't know exactly the origin of color. Again, it's an understudy. So if you guys want to go into the field of gemology, you know, you have a lot to do with colored diamonds. They're rich in hydrogen. So is that the cause of the color? That's actually right now the working hypothesis. Orange diamonds, yes, we gave me those pictures earlier. This is a 14-karat stone sold for $35 million. It's the most expensive orange diamond ever sold at an auction. It's beautiful. I've not seen it in person, but the color is just gorgeous here. And the thing about orange diamond is usually they have a natural luminescence. They emit light at the same time as they absorb light. So it kind of glow a bit like yellow plus orange. So you really receive the color in your eye. It's not only passive, it's really lively. Those stones are usually really lively. I know this stone, and again, when I saw it, it's only 2 carats, but the color of this orange stone, it's pure orange, okay? There was no brown component or no other component. The pure orange is extremely rare in nature. Those diamonds have not been studied that much, or at least not understood that much. What we know is that they are most of the time type 1A diamonds combined with type 1B, meaning that they have isolated and aggregated nitrogen inside them. This is a typical spectrum, and people even think that this absorption bands that provides the transmission in the orange here, this absorption band might be due to some oxygen-related defects. So the defect exactly is not known. It might involve nitrogen, isolated, aggregated, and even oxygen. This is a big question mark here. Green diamonds, well, it's a rare body color, and actually most of the time the natural stones, as in this rough stone that you see here, the green color is only at the outside, on the outside crust of the diamond. So if you want to polish it, the color would be gone. And here, the clever thing that this diamond cutter did is to leave some rough part on the stone to leave this, like, well, it looks ugly on this picture, but still, to leave some green, natural green outside, giving rise to a green diamond. So this is most typical of green rough diamonds. The color is not going to be there because it's only outside. Diamonds, green diamonds that have a body color, strong body color, are really rare. They do exist. For example, that's the case for the Aurora green diamond, a 5-carat fancy vivid green, graded natural. by GIA, and that was sold for $16.8 million in 2016 to the largest world jeweler, Cho Tai Fook, and it was the most expensive green diamond ever sold. Now you probably know about this one, the Dresden green, 41 carats, the largest green diamond in existence. It's a type 2A. And okay, honestly, I've seen it. You know, I've seen many pictures of this diamond before seeing it in person. These pictures don't do it justice. It's a teal, incredible color. It's really beautiful. You can see it at the Green Vault in Dresden. I will, no, actually, no, it's not in Dresden. It's on display at the Met Museum in New York. But when the confinement is over, lockdown is over, it will go back to Dresden, I'm sure. And please go and see it because it's absolutely gorgeous. The origin of the color in those diamonds that have this green color is due to natural irradiation. And this is the peak and the color center, which is called the GR1 center, that allows only the green part of the spectrum to be seen. I'm showing you this spectrum. It dates from 1988, actually, when George Borsat took his equipment to study it at the Green Vault, on site at the Green Vault. He actually created cryogenic units to cool the diamond down to be able to capture this very sharp line. Otherwise, if you were to take this at the normal temperature, you would not see it as well. This color center is called GR1, and it actually one vacancy, so one missing atom, but a lot of missing atoms within the structure, and that gives rise to the green color. The issue is that you cannot make the difference between a natural green diamond naturally irradiated and a diamond irradiated in a lab. I'm running late, I'm really talkative tonight, I'm sorry about that. And I want to finish with blue diamonds, so no worries, I'm gonna finish in 2 minutes. This nice suite of blue diamonds was taken at the Smithsonian. You have two Smithsonian diamonds here, the Blue Heart and the Hope Diamond. This is the Heart of Eternity that was at the Smithsonian for a special exhibit. The Hope Diamond has an entire story by itself. It's the largest blue diamond, pure blue diamond that is in existence. Whole story by itself. I'm not going to go into that. The Blue Heart is a beautiful, beautiful stone, believe me. It's set in a ring at the Smithsonian. So maybe you're not used to see the Hope Diamond like this, but sometimes it's removed out of this setting to, well, for special exhibits or for other purposes that I will show you later. I like to show you this because it compares the Hope Diamond with another historic diamond, that is the Wittelsbach diamond. Both were mined in the 17th century. And both show this strong red phosphorescence. It's not fluorescence, it's phosphorescence. That means that when you put a UV light under the diamonds, nothing happens. Then you turn the lights off and the two diamonds continue glowing like crazy for a minute or over a minute. So these photos were taken at the Smithsonian. It's quite impressive. This is not typical for blue diamonds, actually, the red phosphorescence. So that's why we thought in the first place that those diamonds were cut from the same crystal. And when we did the research, we realized that that was not the case. See, that was the Wittelsbach before it was recut by Graf, when it was sold at an auction at Christie's. So don't worry, it's not that by recutting it, it got worse. No, it's just that it's photoshopped. The color is not real. This is a proper color here of the diamond. And actually you see that's my hand here, and for the size you see the Hope and the Wittelsbach next to each other. You see this huge culet facet through which you can see, this is called a window effect. Another beautiful thing from the Smithsonian, necklace with 9 colored blue diamonds. It's called the Cullinan Blue Diamond Necklace, and was given by Thomas Cullinan to celebrate the found of the Cullinan diamond. So if you're hearing a lot of noise in my place right now, it's because it's 8 o'clock and it's time for people to clap, to say thanks to everybody, to all the people taking care of us at hospital. Blue diamonds, the color is due to boron. They're type 2b diamonds. That means that they contain boron, and that's actually boron that gives rise to the color. Boron doesn't have any color per se, but in the structure of diamond, again, it gives rise to specific absorption, therefore to color. And just to finish here, we had fun at the Smithsonian with Jeff Post and Russell and Chris and Emma over there measuring, and Detlef Ross measuring some boron into the diamond. It was not only to have fun, it was because it was not really done before. And it was the boron content in diamonds was only done by looking at some not really gemmy diamond, not some blue diamonds, mostly colorless or gray type 2b diamonds. That's why we wanted to conduct this analysis. And we did that with a big machine, but this big machine is non-destructive. Before that, if you wanted to know the boron content of a blue diamond, you would have to destroy pretty much the diamond. So we want to avoid that, right? So this is a time of flight secondary ion mass spectrometer in at the Smithsonian. This is me, yes, the time, and Detlef Rost. And this is the Hope diamond within the machine. No worries, it doesn't have a scratch. Other diamond, the blue heart diamond, and actually before we conducted the first experiments were not done on the Hope or the blue heart, they were done on other stones that we didn't, the value was pretty much only scientific. Before we knew from other studies that the boron content was less than 1 part per million. I was telling you about hundreds of parts per millions, thousands of parts per million for nitrogen. Boron, it's only less than 1 part per million, it's crazy. Our studies actually show that it can reach 2 ppm, woohoo, or up to 8 ppm in the Hope diamond. Actually, the concentration of boron is not homogeneous within the stone at all. So don't worry, everything is back. The diamond is put back on this Cartier setting that you see here, and it's all safe. And just to finish here, wrap up the take-home messages. To be perfect or not, it really depends. I want my light to be colorful, so I know the answer for me at least. Take-home messages are those elements that color diamonds don't have color by themselves, okay? But combined with carbon in the structure of diamond, it then absorbs lights and then induce color. Know as well that the fancy vivid color is the rarest of all the fancy, and the fancy diamonds are the rarest of all diamonds ever. Okay, and that's not even talking about, enhancing the color, the treatments, and all of that. So, okay, I will stop here and I will welcome your question. Stop sharing my screen. I know a few people asked me about chameleon diamonds, so if you want to stay a bit later, you can, and I will show you a few slides about chameleon diamonds, but I'm going to stop here and actually see what kind of questions you have for me. I hope that you enjoyed it. I've been long, I'm sorry, but it's a big topic to cover.
You did fantastically well. Thank you very much, Eloïse. Everybody's clapping. I mean, we're hearing the clappings and the sirens of the ambulances. Yeah, well, I'm sure everybody here is clapping. Thank you very much. It was really a really insight, and you make that complicated science look so simple. And it's really nice to have somebody like you explaining complicated things in a simple way. And I mean, we are talking about the most expensive gem materials on the planet, and all of a sudden they have colors because they have defects, which is I mean, they are not perfect, and because they are not perfect, they are valuable. A little bit like people, maybe.
Yeah, that's how I feel about myself.
One of the things, while you are looking at the questions and the comments, I'm sure that you have a lot of them. One of the things that I've learned on this lecture is, I mean, this is the same joke as in the morning. I mean, if the house is the diamond, we are nitrogens. So I'm alone at home. So this is a type 1b. But if I have a guest, and if we aggregate, so it will be a type 1a. And of course, there are several types of aggregation. Maybe if there are some more, maybe it's another type of type 1AA, type 1AB. So it's really nice to feel like a type 1B diamond right now. So I would be a canary yellow diamond in my house. One thing that I would love you to explain,
Yes.
you did it, but it's never too much to repeat, is when a diamond is really young, the nitrogens, they are isolated. And then it takes a long time for a nitrogen here and another one to fell in love, and well, okay, now we can aggregate. So, and it takes a lot of time, right?
It takes a lot of time. So, and it cannot happen while the diamond is at the surface of the earth. So it has to be under this pressure and temperature. So while the diamond is still at 150 kilometers deep or even below that. So we know that it needs the pressure, it needs the temperature. So actually we can go back by looking at the nitrogen concentration and the nitrogen aggregation. We can kind of go back into the temperature at which they form or the time at which they form. So the longer we know that a diamond is going to be old when it has a lot of aggregated nitrogen, while when we see a type 1B, so it's not as old. So people are going to be asking me, so how old is a young or diamond? So basically I say old when it's older than 1 billion years old. We have younger diamonds like for that. So yeah, kind of old.
Interesting.
That's why geologists are interested in diamonds, because they come from very deep and they are formed, most of them, a long time ago. And these are actually the only materials coming from that deep and being preserved, and that we can hold in our hands and study. So that's, for us, is very important.
And by the way, Eloïse, because I gave you the host,
Yes.
now I cannot push any button. It must be you to share the poll. So you have
sure.
to click,
so I have to click the poll.
Click and share it. So
Launch polling. Okay, people.
Looking at it for the first time, because normally
you have allow panelists to vote. Sure. Yes. Can you see it?
Well,
no.
Maybe you.
No poll. Okay. Can I give you back the hands? Maybe.
Maybe it can. Do you know how to do it?
Oops,
oh yes.
Yeah. Okay. Okay. All right.
Now it's the first time I will be able to vote.
Now you know if your questions actually like make sense, you know. That's a good test. So while you are doing that, I'm going to leave the poll for what, like about 3-4 minutes. I can answer a few of your questions if you still have time. If you don't have time, thank you very much for being here tonight. Really appreciate you coming and showing and being reacting and sending a lot of messages. I will try to go through your messages a bit after. I cannot see because it's moving so fast. I cannot see your messages, but thank you for being here. And if you have some time, well, you can stay a bit longer and answer the poll, and I will try to go through some of your questions. If I don't have the time, I won't have the time to answer all, but maybe I can stay a bit later and write to you the answers. I have a question regarding plastic deformation. Can it cause a change in the bonding angle in the coordination of carbon in diamond? That's a very specific question. The answer is yes, in some diamonds. So in brown diamonds, you won't see any local defects. When you look at the atoms, really, you don't see necessarily where it happens. Sometimes you see that, again, it's really this motion that I'm doing, it's really what's happening. So sometimes, yes, at these planes, you can see that the carbons have moved this way. It's called gliding. For some pink diamonds, the ones that show this very strict lamellae, actually not only they glide, but they twinned. So that means that the angle of the atoms completely change within the structure. It's called mechanical microtwinning. So I hope that answered that question. Are white diamonds opalescent because of their fluorescence? That's a really good question as well. I didn't cover that up. Again, 1 hour is definitely not enough. So some diamonds, so I showed you the opalescence of diamond. And for those that show this milkiness aspect due to nano inclusions. But indeed, when you have a very strong fluorescence due to the N3 center, for example, you will see that these diamonds fluoresce indeed. And if the fluorescence is really strong, then it will appear milky. So yes, fluorescence is the cause of milkiness. That's why in the markets, they don't like when your diamond fluoresces that much. Okay. Salt and pepper diamonds are only a name for diamonds with many internal inclusions. Okay, maybe I'm not the best person to answer that question. However, from what I've seen in Tucson over the past few years, the salt and pepper diamonds are the ones that are really included. Maybe I'm wrong. That's only what I know from the markets. What is the effect of radioactivity radiation on diamond color? So what you mean maybe is natural irradiation on the diamond, but that actually can cause a lot of damage to the structure. When you irradiate a mineral in general or a diamond, what you would do, it will actually throw some atoms away out of the structure. So basically some carbon atoms are going to be moving out, and so it's going to leave vacancies. For example, the green diamonds, the green color is due to these vacancies. So these diamonds that have been moved away, so they didn't move out of the diamond, they just moved in an interstitial spot. That's how we call it. So yes, radioactivity has an effect. And then when you combine it to heat, then it can give rise to other color. That's what is done in nature, and that's what is done in the lab as well. That's going into treatment of diamonds, and I really don't want to go into that today.
I have here one question, which I was about to ask you, but Antonio Amant from London, he also asked is, what are the green emitters?
Yes, nice word. I like that you use emitters and not the chartreuse. We call them chartreuse diamond in French as well.
Exactly.
Yes, so these are diamonds that contain the H3 center. Okay, so the H3 center is what, like 3 nitrogen, I think. Like don't quote me on that. The H3 center, and it emits a fluorescence in the green. So that's another defect that you see a lot in brown diamonds. So that's sometimes brown diamonds show this this green fluorescence. Yes. So does that answer the question?
Yeah.
Okay. I thought that the blue diamonds had boron. Okay, well, we'll see that in the poll. Now, 5 minutes poll. Should I close the poll, Rui? Yes, I think no
Yes.
people are.
Eloise, now I cannot see nothing because now you control everything.
Ooh, be careful, I will take...
Yes, I know.
You'll get used to that. Okay, so the first question is, what's the most important in natural colored diamond? Is it...
Oh, click share. Click share, yeah, so everybody can see. Yes.
Yes? Okay, yeah. Good. The first question is about the most important thing in natural diamond. Is it the 4 C's, so the color, the clarity, the carat, and the cuts? Or is it the color, the color, the color, and the color? The answer is number 2. The only thing that truly matters in the natural colored diamond is the color. Clarity, if the colored diamond is really good in color, honestly, it has a few inclusions. Is the color good? Yes. Then it's a good color diamonds. The carat, of course, it's bigger, but is it bigger but less intense in color? I'd rather have a smaller diamond that has better color than a bigger diamond with less color. So the answer is color. What about the cut? Again, I'd rather have a nice colored diamond with nice intense color than a fancy, crazy cut that is maybe perfect and all the facets join, but the color is not as good. So truly it's the color. The color of black and white diamond is mostly due to, and you answered really well on that one, is the presence of inclusions. Yes, big inclusions, big ugly inclusions. I call them the ugly inclusions for most black diamonds. I told you that some black diamonds are colored just by the fact of being really dark. So that may be why it was confusing. And in the case of white diamonds, it was the presence of small, tiny nano inclusions that diffuse light. The color of yellow diamond is due to, that's question number 3, the presence of inclusion. No, the presence of nitrogen impurities, and that you got to that one very well. 92%, yes. The color of yellow diamond is due to nitrogen, either as isolated nitrogen, and these are the really rare type 1B canary diamonds, or the most common Cape diamonds that have aggregated nitrogen, giving rise to the color in the form of the N3 center. The Hope diamond is colored by boron impurities. You got it right, exactly. It's a type 2B diamond, so it contains boron, and the boron gives color. And this beautiful blue color that everybody loves, well, at least I do. White diamond and colorless diamond mean the same thing. False, exactly. You see that I was talking about colorless diamond to begin with, but white diamonds means more milky or opalescent diamond. So yeah, okay, good. I think that's a good one.
You did well. You don't need me anymore.
Please, come on. So
we have 67 questions.
Oh my goodness.
Yeah.
I will try to answer them maybe after. I don't know what's what your schedule is, guys. So we have still a bunch of people here. But so one question is, blue diamonds must be really rare. Yes, they are rare indeed. And they are found not everywhere around the world. I mean, the mine that produces the most blue diamond is in South Africa. It's the premier mine. We know that India produced some blue diamonds, but it's really rare and they don't come from everywhere. So the production at the premier mine, that is the mine that produces the most blue diamond, is like less than 0.01%. So it's rare. Okay, so I have a lot of questions about the blue diamonds, so hopefully now I answer them. Okay, I have a lot of thank you. What's your Instagram page? Don't worry, that who is going to show that to you?
But because I gave you the host thing,
as you cannot do it.
I cannot show nothing. If you try to, by the way, we can take care of this real quick. Click on panelists and click my name, and on the right you see a button. Click it and give me the host thing again. I give you a blue diamond.
Oh, thank you.
And the pink.
Is it working now?
Now I'm host again. Yes.
Yes.
Now, while you are responding, I'm going to share you my screen so you can see the GIA YouTube channel, where yesterday Evan Smith gave a great presentation on the geology of diamonds. So I'd strongly recommend that you watch these 45 minutes of real simple geology and understanding why diamonds are so important as a study material. So it's strongly recommend that. Also let me see. Okay, this is my Instagram page. By the way, if you want to follow me, I would love it. It's Portugal Gemas, or just type my name. But let me check. Okay, this is Eloïse's museum Facebook, Instagram page. So it's really nice. And by the way, let me show you. My favorite opal is not here, but there is an Ethiopian one, which I love, this rhodochrosite. Now, as you see, it's lovely minerals, and there is one opal here that's this one. This one is absolutely breathtaking. So, and she's a PhD on opal, so you can trust everything that is here. She's really a star on opals. And what can I show you more? I also have a LinkedIn, so if you want to follow the LinkedIn, it's okay. It's under my name. Facebook, I don't care much about Facebook, but it's also under my name. What can I say more? Okay, and go to the YouTube channel of GIA. You can watch all the GIA symposium. Every lecture is there. It's absolutely fantastic. Instead of doing Netflix, you can do gemstones with the GIA channel. So back to you.
Okay, I have again a bunch of questions regarding chameleon diamonds. So those are diamonds that actually change color depending on if they are placed in the dark or in daylight, or if you heat them up. So there's no one answer here. And actually this is still a subject, a matter of great research. There's no one chameleon diamond that really look the same. There's some similar features, but again, they're not all the same. So I can show you what host disabled participant screen sharing, so I cannot do it.
Hold on,
But
I will give you the
so,
screen sharing thing.
and maybe people don't know about those diamonds. They're
Okay, now you can.
that are kind of greenish. Okay. Sorry. Okay, here. Oh, this is a mess here. Do you see that or not? Okay. Here, what about this? Can you see those chameleon diamonds I'm talking about now? Here on the right, this is the same stone. On the right here, those two stones are actually the same. Here is the stone after being in the dark for a long time, and this is the stone after putting it in just getting out of the drawer, basically. Another example here is when it's kept in the dark, and then when it's moved to oh, sorry, that's the other way around. Yellow when it's in the dark and green when it's not. This is the normal chameleon diamonds. You have inverse chameleon diamonds, meaning that's exactly what I was telling you. Sometimes they're green when in the dark and yellow when in visible light. So you have plenty of different kinds of chameleon diamonds, and there's no real answer to what the origin of the color is. I can show you this spectra if you are interested in. It basically shows that when you heat the diamond, you have the 800 nanometers band that is reduced, and that you can see a bit more yellow than before. But honestly, it's a full story by itself, and you will see that in the references that Hui is going to give you when I will give back the hand on it. Then you will have all the references, and then you can know more about it. So you can learn more about it by yourself. And I'm sorry. So these are about, interesting. I can't do it anymore.
What do you need?
No, to give you back the hand. You have the hand right now?
I have everything.
Oh, you have everything. That's
yes.
Okay.
I was going to, by the way, I will try to put some links on the chat, but yes. For security reasons, I have no idea why, but Zoom does not allow clickable links anymore on the chat. So I will put them there anyway, but you will not be able to click them, but you can copy paste them and maybe try to do it somewhere. Anyway, tomorrow you will receive an email with all the relevant links with the articles that Eloïse prepared for you. So I'm putting them on the chat right now. You won't be able to click them, but you can probably copy paste them and work them out later. But anyway, tomorrow you will receive an email with everything, and also with the links for the Tuesday's webinar on not historical rubies, but rubies a long history, historical review.
And I see that there's a lot of questions regarding mostly geology and things like that. So again, go and watch Evan Smith lecture on the GIA website. I have, for example, can alluvial or marine diamonds be identified from kimberlite diamonds? They're the same. They come from kimberlite in the first place. But again, Evan is going to explain all of that to you.
It's really worthwhile watching that.
We covered a lot. I mean, some questions are not really in my area of expertise, such as the different cuts of diamonds in the 16th or 17th century, but I think that Hui is more an expert on that, like the history of like diamond cutting. I really cannot answer you on that. So a few questions I really can answer. Question about prices. I don't know anything about prices. All the diamonds that I've studied were priceless because they were not for sale at the time that I studied them. So I really know nothing about prices. I don't know anything that happens in the labs, you know, I know a few procedures, but I won't be able to answer on procedures. Again, if you have really lab-specific questions, the GIA, or even in France, the Laboratoire Français de Gemmologie can answer those questions for you.
By all means. And the Laboratoire Français de Gemmologie, the laboratory in Paris, is the oldest operating laboratory. Still, it operates since 1929, so it's quite old, older than me. So,
and they do really good research as well. It's not only a lab where they can they just analyze the stones. They actually do active research and they publish. Absolutely. So they're really up to date on everything.
So I think we must end the video session right now. I don't know, Eloïse, if you will be able to stick around offline for a few more minutes. So
yeah,
you can,
I will try to go to the Q&A. I'm sorry, I won't have maybe the time to go to the chat though. I will try to go through the Q&A and type some answers to the ones that I can answer. So again, I will be here around here for the next 10 minutes.
Yeah, well, because we were almost for 500 this afternoon, so it's a lot of people. So it's impossible to greet everyone. But anyway, I can greet you, Eloïse, and thank you very much for having accepted this invitation. You are absolutely brilliant, and you don't need books to look smart. So it's, it was really nice.
Thank you to all of you, all the Americans and the Asians and the Australians and the Africans, like everybody, the Europeans, everybody was there. So it's really great. And I know Hawaii was there as well. So yeah, that's cool. All right. Thank you for joining. And I hope to meet you soon. You can come and visit the museum and we can meet then.
Absolutely. Visit Paris next time, but make a stop in Lisbon. But make surely a stop in Paris, visit the Eloïse Museum. It's absolutely amazing. And thank you very much for being there. Thank you, Eloïse. And thank you, CIBJO, for the support and so enabling us to have a bigger room with hundreds of people joining together and having a nice evening or morning on Gemmology. So bye-bye, Eloïse. Thank you very much.
Thank you all. Thank you, Rui. Bye.
And thank you all of you. Stay safe.
Stay safe, stay home.
Yeah. Okay.
Bye.
Bye-bye. Cheers.